Thank you for your attendance. My name is Alessio Lombardi, and together with Ahmed and Elnagar, representing this work called Title Block Detection and Information Extraction for Enhanced Building Drawing Search. We work for Buro Happold, which is a worldwide engineering consultancy based in London, UK. And for this research, we collaborated with Birmingham City University too. The main problem we are looking at is in many cases, drawings are still one of the main formats of information exchange in our industry. And we can have, for certain projects, especially for historical projects where we have to refurbish an existing building, there may be hundreds or even dozens of thousands of drawings where information is difficult to find. This means that, for example, when you have to refurbish a project like the Barbican in London, which is a project we're working on, engineers will have to manually find and open certain drawings to find information that they need to do the design. Typically, the way we receive the drawings are in piles of literally paper sheets that get scanned and then archived. And the archiving structure can be hierarchical, taking basically a logic that is kind of arbitrary. It can be by discipline, for example, structural or facade or MEP plumbing, or by building area or by type of drawing, level, and so on. This means that, it can work for avoiding duplicates, but for finding information is actually quite difficult. Therefore, we looked at how engineers are searching for these drawings. They typically use the file name if it's possible to find information in there, but in reality, what ends up happening is that they open the drawing and they look at the title block area, which, as you know, is this tiny sliver in the corner, typically, that describes the content of the drawing itself. But the title block, especially when it comes to historical projects, are not regular. They are quite irregular. They do not follow standards. There are standards, but they are not often followed. And there can be also overlaps between the drawing content and the title block itself, which complicates, it makes quite difficult to understand. So we had a look at existing approaches against this problem. We kind of did a literature review with a categorization of existing approaches where we we identified two main problems, two main tasks. Task A, as we call it, is the identification of the title block, and task B is the extraction of the information from the title block, which is then useful for identifying a certain drawing. For both cases, we look at non-data-driven approaches and data-driven techniques like neural networks. We did a comparative study building a small test sample initially with a representative of the variability of the title blocks themselves. Typically, irregularities, hand-drawn title blocks are common with hand-written text and a mix of them. Here are some examples here on the right. This is just a small sample of them. And for the non-data-driven approaches, which are mainly basically based on heuristics or classical machine learning approaches, we examined some of the works that we list here. I'm not going to go into details. Presentation is quite long. And our conclusions on the non-data-driven approaches, where we tested things like dbScan, template matching, or adaptive thresholding, found that, they can behave well for cases where there is a clarity on the title block, especially on CAD-produced, like computer-aided design-produced drawings. But in many of our cases, they actually didn't work. The accuracy was below 50%. So we looked then at data-driven approaches, including the GNNs, layout parsing, table transformer, MTL tabnet, in the assumption that the title block can be thought of as a table, essentially, where there is a sort of structure like rows and columns. We also looked at multimodal language models like GPT-4o and existing tools for similar tasks to this one here, which included Azure AI Document Intelligence, which is built for something like this. What we found is that, these kind of methods, for example, for the table transformer MTL.NET, the fine-tuning required many examples in order to be accurate, and even in those cases, it wasn't easy for us to extract accurate text. We didn't find any good results. For tools like AI Document Intelligence, we have a limitation given by the fact that they are mostly built for regular tables where you need to label each cell of the table individually and give examples very precisely with that. But again, it was time consuming and it didn't cover quite the variation of the edge cases that we had. So instead, when we got to language models, GPT-4o, we did some prompt engineering where we essentially asked GPT-4o to look at both the main tasks that we categorized, task A, the extraction, the finding the title block, and task B, extraction of the information from it. These are some examples of the prompt we tested. We tried some zero-shot and few-shot examples. What we saw is here on the right, basically the results were better than any other approach that we tried so far. However, the text was still quite noisy, and it could include part of the text that came from the main drawing content rather than the title block alone. So the hallucinations were quite common in detecting what the title block was. So we started to formalize the hypothesis as our method as we can split these in two parts, where basically we can use GPT-4o to identify the title block, to extract the text from title block, and manually extract the title block as a test, like imagining that you could try to identify title block as an object detection task. In this case, we have some measures with which we used it. I can talk in more detail, but essentially we measured a very good accuracy with this approach. Therefore, the object detection task, the first task was formalized as object detection, and GPT-4o was used for task B. So for the implementation, I'm going to pass the word to my colleague, Ahmed and Elnagar.
Hi, everyone. So I will just briefly go over how we applied everything that Alessio just mentioned, starting first with the dataset. So we are working with a dataset of around 1,300 drawings, mainly from the facade engineering domain. However, for the purpose of this work, it was sort of domain independent, so it could work for structural engineering drawings, MEP, and so on. So this is an example of the annotated drawing here. We have 4 categories identified: title block, main content, legends and notes, if they exist. And these annotations were done by our engineers using PDF markup software that is widely used in the engineering domain, which is also used by our engineers, so to facilitate and kind of help them do their annotation without having to use some kind of external software. So they would use an environment they are familiar with, and to then convert these annotations into a format that can be used by a neural network. We use a simple Python script to convert these labels or the annotations into a COCO dataset, which is then fed into the neural network. Neural network we chose was Faster R-CNN with a ResNet 50 backbone. So the reason we chose this and not something bigger like a YOLO V11, V12, and so forth, is that our application, it was not that complex. We were just doing object detection. We did not need segmentation for this task specifically. So for the sake of saving computational time and effort, we just decided to go with a Faster R-CNN, and the results kind of speak for themselves. We got an accuracy of over 97%, so we were doing quite well. And yeah, to distinguish between true positives and false positives, we were using intersection over union. And over here is the combined pipeline. So we start with feeding a drawing into the neural network, conduct inference. We get a title block out of that. We extract the title block, so we crop it, we encode it, and then send it to our deployed instance of GPT-4, so our LLM. The LLM then extracts the information from the title block. As Alessio mentioned, the prompt that we were using was splitting the text into the key value pairs depending on the cells. So it would group the cells together, or the text in the cells together. And then using some semantic text processing, we were able to also group similar keys together, so to cluster them together. For example, you can see here we were grouping things like drawing description, and DWG, DESC together, since they represent the same thing, to avoid having redundant keys. And following now, we have the database of all the drawings for, so in this example here, we are using the Barbican refurbishment project, which Alessio mentioned earlier. You can see here we were grouping project name with other keys, and then drawing description, and so on. And then on the right here, you can see the drawing names, and then all of the project names extracted from them. And to package all of that together, we developed a very simple app for the users to be able to search through all of these drawings. In this case, we had thousands of them. It's quite simple. They would just input a search query using the usual operators such as and, or, and so on, and they would just get a list of drawings matching their search as an output. This can obviously be easily integrated into a chatbot or into the search functionalities that the engineers already use. And lastly, the Barbican project that I mentioned earlier. This is a refurbishment project from the 1970s, or it was built in the 1970s. We had over 6,000 drawings there. So for the engineers to find a specific drawing or drawings that they are looking for, it was very time consuming. By using our work, they were saving, so by using we had some usage analytics, we determined that we were saving at least 40% of their time for searching for drawings, and in some cases up to 80% as well. Alessio will then just quickly go through the future works.
Thank you. Yes. So as you can see, our tool was used internally for a project. So we actually saw the value that was added from our tool. For the future, we know that there are some limitations of our work. In particular, for search, it would be useful to look at the symbols contained in drawings. That's something that we would like to look at next. We would like also to expand to drawing understanding, and particularly using like knowledge graphs or ontologies to represent the content of the drawing, in approach similar to scene detection in computer vision, for example. I'm going to just briefly mention that we looked at existing ontologies, and particularly also a tool that we have internally, the BOM. The BOM is a framework that we developed and published open source that can represent particular concepts in the industry, also non-geometrically related concepts like forces, stresses, temperature exchanges, and things like this. It's designed for the engineering industry, and it has parallels to ontologies and other formats like FC and other tools. So yeah, this is a subject of another part of the research. And yeah, for compliance checking also, it's another area we would like to look at. It's very complex naturally. It will be another completely bigger kind of problem to solve. But there are some particular use cases that we have internally where we would like to look at, and we think it's doable to try to solve. And that's all. Thank you, everyone.
Great. Thank you very much. Do we have a question from the audience? I don't see one. Oh, two. Darn. I'm going to give Andre first pass, and then you, Jörn.
Okay, anyways. Hello.
Hey.
So thank you very much for your presentation. So, I mean, like the question that I have is more just, just to further educate myself, because, like definitely with regards to computer vision, like normally when it comes to my mind, I usually think, like straight up CNNs. But, like looking at this presentation and as well as like the other ones in this track, I mean, like you guys and as well as like a lot of others, like you're using kind of LLMs and CNNs, simultaneously. So, I mean, just to kind of further my understanding, if they're both used, to conduct a computer vision-based tasks, what's like the best use case for one or the other? Because, I mean, like, to me, it looks like they are both able to, interpret images and look at shapes and all that.
Yeah, so. Thank you for the question. Yeah, that's a very good question. The reason why here we formalized it as Liz is also because we think we want to expand the data set that we built for other tasks that are more computer vision related. So we noticed that these can work for this particular use case, but we believe that particularly for symbol detection or segmentations that we would like to do next, we would like to expand this data set to that kind of things. So yeah, the split. Also using like even a few shots with GPT-4o didn't really prove useful. There were many hallucinations, so the reliability of just using one or the other, I think they complement each other quite well. Yeah.